Sprawling across hundreds of acres, this high-security complex is America's center for directed energy weapons production.
Behind these walls, we revolutionize defense technology. Our precision manufacturing processes create the most advanced directed energy weapon systems in the world.
The data confirms a significantly lower cost per engagement, and as the video demonstrates, level 1 effectiveness against hypersonic forces. We must ensure these systems share target data seamlessly across all branches. The Navy's tracking must integrate with Army ground assets.
The radar signatures look stable, but we still have a conflict on the primary laser frequency.
Adjusting the waveform parameters now.
The speed and maneuverability data on the new drones changes the calculus immediately.
Agreed. The laser defense grid neutralized 70% of the incoming swarm.
That significantly reduces our asset exposure at the
The atmospheric turbulence model shows a 15% improvement in beam stability with this architecture.
This adjustment to the resonant frequency improves the coupling efficiency.
That data confirms the scalability for the directed energy application.
Our industrial base is rapidly scaling up production of these advanced systems, ensuring we meet the rising military demand.
Our analysis shows the laser system drastically lowers the cost per engagement.
And this sustainment plan optimizes.
The electromagnetic emissions are within acceptable limits. Good.
Now we finalize the high-voltage safety protocols for the deployment team.
These directed energy weapons provide a revolutionary defensive capability designed to protect our personnel and assets.
Doctrine must emphasize the organizational structures needed for this transition.
Agreed. Training is paramount to maximize speed and magazine depth in theater plans.
The atmospheric disturbance is still affecting the beam integrity at this range.
We need to recalibrate the adaptive optics in Sector 4.
Megawatt class output confirmed. Successful demonstration, gentlemen. This validates the technology readiness for transition.
The beam combining architecture is holding stable at 100 kilowatts.
Power up converter 2. Let's see if we can reach the target threshold.
Initiating sequence now.
Tracking missile Alpha. Beam solid.
Thermal bloom detected. Structural failure. Splash. Shifting to Bravo. Beam on target. Splash. Good hit.
Target acquisition successful. Engaging swarm sequence. Multiple kills confirmed in under 10 seconds.
Turret deployment sequence initiated.
Movement is nominal. Testing the 360 slew rate.
Data links are green.
Power flow looks stable at 50 megawatts.
Initiate the stabilization sequence on my mark. We need to align the field of fire.
The integration facility ensures these systems are ready for rapid global deployment. Mobility testing confirms stabilization.
We have reduced output power. The flowchart points to the diode array.
Confirmed. I'll retrieve the spare from logistics.
Post-installation tests show nominal performance.
Optics cleaned and verified. Ready for reinstallation.
Diagnostics complete. System performance is nominal. Finalizing the log entry.
Designating laser engagement on incoming threats.
Tracking successful.
Battle damage assessment confirms neutralization.
Incoming simulated threats, bearing 290. Tracking initiated. Weapon systems 1 and 2 active. Engagement ready status confirmed. We need to verify optical alignment using the power meter before proceeding.
Confirmed. Should I reference the cooling system manual first?
Yes, follow the diagnostic procedure exactly.
All right, everyone. Section 3 covers engagement procedures. Ensure the system is aligned before activation.
Control. Alignment sequence initiated. Weapons free. Engaging targets sequentially.
Confirmed structural failure on both targets. The weapon system is effective.
Safety protocols confirmed. Range clear. Beam director slewing to coordinates. Power systems are online. Tracking confirmed. Initiating simulated engagement sequence. All parameters green.
The bore sight alignment is off by 2 microradians on the azimuth axis.
Adjusting the gimbal mount now. Verifying.
Lowering sequence engaged. Watch the alignment pins on the starboard side.
Alignment confirmed. Commencing torque sequence on main bolts.
Set the torque to the specified value in the manual.
Roger that. Applying final torque now. We need these pads ready for the laser mounts by 1500.
Electrical and water lines will be fully integrated by 1400, sir.
Hold that unit steady. We're clear to move it. Copy that.
Bringing it to the inspection bay now. Sensors indicate proper humidity levels maintained.
Bills of lading match the manifest.
All checks complete. We are clear to roll.
Copy that. Moving out.
Serials match the manifests. Character C, ready for final authorization.
Export compliance confirmed. Clear this shipment for loading.
All right, lower easy. Inspector, confirm the desiccant placement. Check. All specifications met, ready for final seal.
Covers installed, checklist verified.
Humidity control purged and sealed on Unit 7.
Documentation secured, ready for shipment.
Digital systems link every component to its source, every process to its procedure, and every test result to its requirement.
The demonstration confirms the laser output meets the threshold requirement.
Verified.
Verified. Simulating cooling failure now. Stand by for results.
System shutdown confirmed. Response time logged.
Thermal imaging confirms steady state operation. No anomalies on the optical path. Data logs confirm stable power output and beam quality throughout the run.
Temperature stabilizing at +60. Cooling systems maintaining optimal performance. Check beam quality.
Beam quality.
Look at the resonance on the gimbal mounts. It's higher than predicted, but still within the threshold. Alignment sensors confirm stabilization after the impact sequence.
Initiating the immunity sweep sequence. Levels are nominal. The system is stable, no degradation reported.
Turbulence is spiking as expected.
AO system engaged. Look at the wavefront correction. Power transmission stabilizing. The system initiates the ablation study, directing focused energy onto the composite samples to measure material response and penetration depth.
Beam quality metrics exceed the threshold.
Confirmed. The system meets all key military specifications.
Reading surging, approaching maximum threshold. Initiating stabilization sequence. Interlocks engaged. Cooling system status?
Flow rate nominal. Calorimeter stabilized.
Power levels stable at 10 watts.
Confirmed. Beam profile looks nominal.
Hold position. Lowering subsystem now.
Clearances look good. Set it down slow.
The team integrates the control electronics, programming the firing logic, and testing the safety systems that coordinate the entire laser weapon operation.
Initiating simulated load test. Monitor the thermal sensors closely.
Power draw is stable. Cooling systems are maintaining optimal temperature.
Beam profiler looks stable. Power output is nominal. Good.
Let's lock the mounts and initiate the purge sequence.
The alignment on the polarization combiner looks good.
Power efficiency is stable at 98%.
Using electron beam evaporation, we deposit materials like titanium dioxide with nanometer precision. Using automated systems and specialized laps, we achieve angstrom-level smoothness, verified by laser interferometers projecting fringe patterns.
The process begins with precision grinding. CNC machines utilize diamond wheels to shape the lens blanks.
The burn-in process rigorously screens for early failures, running devices at elevated temperatures and currents to ensure long-term reliability. Hermetic sealing protects the laser diodes. Afterwards, helium leak testing verifies the seal integrity, crucial for military-grade performance. Precision dicing saws cut the wafers with micron accuracy. Then, cleaving tools separate the bars, creating.
The wafers undergo backside processing, moving from automated grinding and polishing to backside metallization.
In this ultra-clean environment, automated systems meticulously prepare the semiconductor wafers, a critical
Deposition. As the pressure drops into high vacuum, the plasma ignites, signaling the start of deposition.
Openers. The wafers undergo fine polishing, achieving a mirror finish. They are then inspected with interferometry.
The boules cool under a purified argon atmosphere. Advanced inspection systems detect microscopic defects.
Initiating extraction sequence. Maintaining the specified pull rate.
Confirmed. Temperature and argon levels are stable.
Directed energy weapons, once science fiction, are now an operational reality, defending freedom and security across the globe.
Thermal regulation is holding steady in the cold chamber.
And the corrosion resistance passed the sand ingestion test.
Force. The autonomous system handles tracking, but the final engagement decision rests with the operator.
Diagnostics report is green across the board.
Calibration complete. System is fully operational. The applied research data confirms the increased output efficiency, and the simulation shows the atmospheric effects are minimized at this wavelength.
We've completed the assessment of the nominal hazard zone. The OD measurements are confirmed.
Verified. Your procedural.
Looking at section 4.2, the definition for effective range needs revision to match the new testing protocols.
Agreed. That ensures consistency with the safety parameters.
That concludes the overview of deployment challenges.
How did the humidity affect the beam stability?
We saw a slight decrease in range, requiring a change in tactics.
Fielding these systems changes the deterrence calculus significantly.
It stabilizes theater defense, but we must account for the accelerated arms race dynamic.
Public sentiment is shifting positive on the energy programs.
Good. Let's highlight the humanitarian applications in the next briefing packet.
This confirms the dual benefit, national security and substantial economic returns.
The projections for Q.
Congratulations on behalf of a grateful nation for your groundbreaking work. Thank you, sir.
Look at the efficiency gains in the solar sector just from the power management transfer.
Exactly, and the advancements in ophthalmology utilizing the beam steering tech are unprecedented.
From early experimental systems to modern solid-state lasers, this exhibition documents the long-term.
This housing is clear. Where do you want the doped optics?
Place them in the yellow bin marked for hazardous materials disposal.
Before delivery, every laser weapon undergoes comprehensive performance verification. Our quality gates ensure 0 exceptions.
The energy output stabilized significantly.
Agreed. Beam quality metrics show clear improvement.
We should share this data with the evaluation team immediately.
The CFD models were accurate. We're seeing significantly improved heat removal efficiency with the new microchannel design.
This failure detected on the primary oscillator. Root cause appears to be voltage instability.
Agreed. Adjusting the calibration parameters now. Ramping power back up. We need to verify the end-user certificate on this laser system transfer request and confirm the ITAR guidelines are met before we approve the disclosure.
You hesitated on that target right there. Identify the priority threat faster next time.
We need immediate neutralization.
Multiple threats incoming, Vector 7 Alpha. Engaging with directed energy.
Kinetic interceptors authorized for priority targets. Launching now. Adaptive optics stabilizing the beam. We have a clean shot.
Engaging target now. Confirming atmospheric distortion minimized.
The scintillation data correlates directly with the high altitude wind shear.
So the model accurately predicts turbulence effects in this environment.
Sir.
Sir, this section on non-lethal application needs revision.
Based on the recent Hague commentary. And we must emphasize...
Look at this optimization curve. The adaptive optics compensation is stabilizing the wavefront. That's a 20% improvement in power delivery.
The predictive model flags an issue on System 7. Component degradation detected.
Run a virtual diagnostic. We need to optimize the calibration remotely.
We need to standardize this workstation layout.
Agreed. The motion study shows too much wasted movement here.
Let's update the visual aids to reflect the new process.
The stockpile visualization shows 45 days coverage on rare earth elements.
We can publish the support structure, but the beam amplification process must remain a trade secret.
Agreed. That balances our portfolio while protecting the core IP.
Test sequence complete. Initial data suggests high fidelity.
Simulation prediction aligns perfectly with the measurements.
This modular design enables technology insertion throughout the weapon's service life.
We can swap the sensor package without redesign.
This component is over-spec'd for this subsystem. Simplifying the housing design will reduce machining time and costs significantly. The quantitative analysis confirms our technical risk exposure on the high-energy optics.
But the mitigation strategy...
The impact analysis confirms the change is feasible, but we must update the specifications immediately.
Understood. We need to finalize the power output specifications before the preliminary design review.
Turbulence. We've achieved closed-loop correction. The deformable mirror is comping for the simulated atmospheric turbulence.
Balancing military capability with proliferation concerns is the main challenge here.
We must ensure the policy aligns with international humanitarian law.
This configuration seems stable for the initial targeting sequence.
The visual cues are clearer, but the haptic feedback is still lagging under stress.